Hi everyone. So this is going to be the first Math 103 lecture in the video format. And I'm going to actually post the lecture notes that are associated with this video as well. So you don't need to save the screenshots or take pictures or anything of the boards. So this week we're going to cover Chapter 10 content. And Chapter 10 in the book is about sequences. And so this is officially lecture number 19. So let me start by defining what a sequence is. So a sequence, by definition, is just a list of numbers. Is a list of numbers. In this course, rather in this module, our sequences will be infinite. So we'll be dealing with infinite sequences only. So we will deal with infinite sequences only. Because later on, we'll talk about convergence of sequences and divergence of sequences and things like this, which only make sense for infinite sequences. So let me start by giving examples of sequences. So, examples. So for example, we could have, this is number 1. So we can have the sequence 1, 2, 3, 4, so on. Here's another example. 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. We could have, for example, the sequence of alternating 1s and -1s. So 1, -1. So we can start with 1, -1, 1, -1, and so on. So as we can see in these examples, I have just given the first 4 numbers, right? So in these examples, we have only listed the first 4 numbers of the sequence, because the rest of it you can guess, because you can guess the rest. But somehow this is not a very comfortable notation, because we don't want to be just writing down terms of the sequence. So like in this in this sequence, in these examples, you could guess the rest of them. So here we have 1, 2, 3, 4, 5, 6, 7, so on. And here you're just taking the reciprocals of the numbers. But somehow we want to have the convenient notation or compact notation to denote the sequence. So a more compact notation is to just specify what the nth term of this sequence is. Specifying the nth term of the sequence for each value of n. And that would do it for each n. Okay, so what I'm saying is every sequence, we already know that every sequence looks like this. So we have A1, A2, A3, A4, A5, and so on. And therefore, in this notation, so thus, A sub n is supposed to be the nth term of the sequence. So by giving a formula for a sub n, we can describe the sequence more efficiently. So in the book, sometimes they start at the index 0. So for us, the notation a sub n bigger than or equal to 1, will be basically a shorthand for the sequence, A1, A2, A3, A4, so on. The book starts at 0, but it's just a convention. So in the book, you can see, so in the book, in some of the examples, we're also going to use this index, n equals starting at 0 is used. So the first term is a sub 0, but this is a minor difference. Okay, so let's go back to our previous 3 examples. Going back to the 3 examples above, we can now describe them more efficiently. So example 1, we had 1, 2, 3, 4, and so on. So this sequence can be described by a sub n, the nth term of the sequence, is simply n, right? Because by definition, a sub 1 is the first term, so this is like the first term, a sub 1, and according to our formula, this is just 1. This one is a sub 2. According to our formula, this is just 2. And so, as we can see, our sequence is just this one. So we write n to indicate this is the nth term, and then we write n starting at 1 to indicate that our variable starts at n equals to 1. Of course, n here is just a dummy variable. We could have just written this as t, where t starts at 1, for example. All right, but usually we use the letter n in the context of sequences. So let's do the other sequence that we had, which was 1/2, 1/3, 1/4, 1/5, and so on. So I want to describe this using a formula, which means that I need to figure out what is the formula for the nth term, and we see that it's just a reciprocal of a number, and it's going to be, in this case, 1 divided by n plus 1, where n starts at 1. And so we see that, for example, if n is 1, we get a sub 1, the first term, so it would be this one. So a sub 1 is the first term, 1 over 2, because that's what happens when you plug in n equals to 1 into this formula. And similarly, this one would be a sub 2, 1 over 3, because if you plug in n equals to 2 into this formula, you get 1 divided by 2 plus 1, which is 1/3, and so on. So describing a sequence in this compact way is very useful, because first of all, it's much shorter, and it's more precise. Because if I just give you first 4 numbers, maybe there's some mysterious pattern behind this, in addition to the obvious one, but somehow by giving a formula, we kind of have fixed what the sequence looks like for every term. And so there's no ambiguity. There's an ambiguity if you write it this way. There's no ambiguity if you write it this way. Okay. Let's write down the third one. So the third one is the sequence was 1. Oops, sorry. Just go back. So the sequence was 1, minus 1, 1, minus 1. And if you look at this sequence, then we can describe this as minus 1 to the power of n plus 1. That's going to be my formula for my nth term. Okay, great. So that's that. So what is another way to construct sequences? Another way to construct sequences is using functions. So the useful way to construct sequences would be as follows. So for example, we can have a function f, any function we like. So suppose f of x is any function, let's say with domain real numbers, whose domain is all real numbers for simplicity. Domain is all real numbers. And we can describe a sequence just as follows. So we can define the sequence a sub n by f of n. So I'm basically plugging it in natural numbers into f of n. So for each n starting at 1. So for example, let's say I pick the function, let f of x be x squared plus 1. Then we get the sequence defined by, a sub n equals to n squared plus 1. Because I'm getting f of n, but f of n is, let's write this more clearly, so we're getting a sub n equals to f of n, and that is n squared plus 1 for each n. In other words, I have defined a sequence whose nth term is given by the formula n squared plus 1. So if you write down what a sub n is a list of numbers. So when you plug in n equals to 1, we get a sub 1, and that's 1 squared plus 1, that's 2. When you plug in n equals to 2, you get 2 squared plus 1, and that's 5. You plug in n equals to 3, you get 3 squared plus 1. So a sub 3 is 9 plus 1, which is 10. Okay, so then we get 17, 26, 37, so the basically squares plus 1. So that's my list of terms for this particular sequence. Okay. So I want to point out that sometimes two different functions can give us the same sequence in this way. So for example, let's consider the functions f of n equals to n, and g of n, it's another function, equals to n, that's not what I meant to say. F of x equals to x, and g of x equals to, again. So let's consider the function f of x equals to x, and g of x equals to x plus sine pi x. So these two functions are clearly different. However, if you define the sequence a sub n by f of n, and if you define another sequence b sub n by g of n, then in fact, even though the functions are different, in fact the sequences are the same, because what is a sub n? Well, a sub n is just n, so this sequence is just 1, 2, 3, 4, and so on. Well, what about b sub n? Remember, we're plugging it in integers, right? So b sub n is, by definition, n plus sine pi n. However, sine evaluated at integer multiples of pi is identical to 0, so this is just 0. So we still get that b sub n is equal to n, which again leads to the sequence 1, 2, 3, 4, and so on. So in other words, even though the functions are different, they can give rise to the same sequence. So the above example shows the example shows that different functions can give rise to same sequences. Okay. Now, here's a remark. Note. So not all functions, not all sequences need to have nice formulas. Need to come from nice formulas. So need to have nice formulas. So far all the examples I described, they all have nice formulas, but they don't have to. Okay, so let's consider the sequence defined as follows. Defined by, so I'm going to tell you the formula for the nth term. The formula is not given by a function, it's just some piecewise defined thing. So a sub n, in other words, this is the nth term of the sequence. In other words, this is a sub n is 1 if n is a power of 2 and it's minus 1. It's 0. It's 0 if n is not a power of 2. So what is a power of 2? Well, power of 2 is just anything. So by definition, power of 2 just means n is of the form 2 to the k for some integer k. Let's say starting at 0. For some integer k, which is at least 0. So this is a perfectly well-defined sequence because I'm telling you what the terms are. So let's write down the terms of this sequence. Okay, so let's write down the terms of the sequence. So a sub n and at least 1. So if you want to write down the sequence, well, by definition, it's a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub 8, a sub 9, and so on. Okay, so so let's see. So the first term, a sub 1, well, according to the definition, it's going to be 1 if the index, namely 1, is a power of 2. And it's going to be 0 if n is not a power of 2. Well, in this case, for the first term, n is 1. Is 1 a power of 2? Yes, because 1 is 2 to the power of 0. So because n is a power of 2, a sub 1 must be 1. So a sub 1 is 1. A sub 2, we have to look at 2 and see if it's a power of 2. It is. 2 is 2 to the power of 2. So we get 1. 3. Is 3 a power of 2? No. So we get 0. 4. 4 is a power of 2, so we get 1. 5 is not a power of 2, we get 0. 6 is not a power of 2, we get 0. 7 is not a power of 2, so we must assign 0. 8, though, is a power of 2, because 8 is 2 to the power of 3, so we get 1. And then 9 is 0, and so on. Up until, of course, 16 is going to be 0. So you're going to see a 0 at the 15th slot. N equals to 15 will be 0, because 15 is not a power of 2, but then n equals to 16 will in fact give us 1, because 16 is 2 to the power of 4. Okay. So you see that in this case the formula, there's no nice formula. So another way to define sequences is known as recursion, using recursion. So this is known as recursive sequences. So what is a recursive sequence? So a recursive sequence is means that the formula for an, so the formula for the nth term for a sub n involves information about the previous terms, about a sub n minus 1, or even a sub n minus 2, or a sub n minus 3, etc. So it just involves some information about the previous terms. So to specify a recursive relation, or to specify a recursive sequence, what we need is the following. We first need initial values. So we know where to start. We must provide some initial values so we can get started, and we need a recursive relation that tells us how to obtain the next term from the previous one. Okay, so we need initial values to get started, and then recursive relation will tell us how to find the next terms. So let's give an example. For example, you can define the following recursive sequence. A sub 0 could be 1, and a sub n would be defined by taking the previous term, a sub n minus 1, squaring it, and then adding 1 to it. Okay, so what does this mean? So let's write down the first few values of this sequence. So we have a 0 equals to 1. That's the first term by definition. A sub 1, in other words, the term corresponding to the index 1, is defined to be a sub 0 square by definition plus 1. So this is just what I wrote down here is simply applying this formula in the particular case when n equals to 1. So we get a sub 1 equals to a sub 1 minus 1, which is 0, a 0 square plus 1. Okay, well then that tells us how to find a1, because I just plug in a equals to 0, a sub 0 equals to 1 into this relation, so I get 1 squared plus 1, that gives me 2. So a1 is 2. If I want to find a2, again I use the recursive relation. So I get a2 is a1 square plus 1. And that is 2 squared plus 1, which gives me 5. So a2 is 5. Let's do a few more terms. So if I want to find the third term, well, rather the fourth term, because we started at 0. We started at a0, so if I want to find the fourth term, which is a sub 3, I plug in n equals to 3 into this formula, so I get a sub 2 squared plus 1. But because I have information about a sub 2 already, I know that it's 5. I get 5 squared plus 1, which is 26. That tells me that a sub 3 is 26. And then a sub 4 is a sub 3 squared plus 1. And so that tells me it's 26 squared plus 1, which happens to be 677. So a sub 4 is 677. So you can see that terms are getting bigger and bigger really fast. So I'm not going to write down more terms. But basically the sequence above, right, the sequence above is this one. A sub n is at least 1. So we have figured out the first few values. So 1, 2, 5, 26, 677. And I didn't calculate the next value, but it would be the following. It would be 677 squared plus 1. And so on. Whatever this value is, then you would have to square it and add 1 to get the next one, and so on. Okay. Now, there's actually a similar construction known as iteration of functions. And this is not written in the lecture notes, but it's important. So this one is not written in the lecture notes that I'm providing in notes for this video. I'm just writing this here just in case you're following along and you're not seeing this being in the notes, so you don't get confused. Okay. What is this? Is the following. So basically, f could be any function. So f of x is any function. And we specify initial value. So x sub 0 is some initial value. And then we obtain the x sub 1 as applying the function f to x sub 0. And then we get x sub 2 by applying the function f to the result of applying f to x0. So x sub 2 is f of x1. But what does this mean? If you replace x1 itself was f of x0, we get that x2 must be f of x sub 0, right? So this is known as iteration. I'm iterating a function twice. So let's look at x sub 3. X sub 3 I want to define recursively, like by applying f to x sub 2. But that's the same thing as applying f2. I know what x sub 2 is from the above relation. So this is like applying f2 to f of x0. So we see that the sequence under consideration is the following. So the first term is x0, this is our initial value. Then we have x sub 1, which is f of x0. Then my next term is f of x0, and my next term is f of the previous term, so f of x0, and then I have f of f 4 times 0, 1, 2, 3, 4, and so on. So this operation of composing f by itself many times is known as iteration of functions. So iterating function just means applying f to itself many times. Iterating a function f just means composing f with itself n times. F with itself n times. Okay. So you sometimes have a short notation for this. I'm not sure if I want to write it. Basically, like composing f with itself means doing this, where little circles just means compositions n times. And sometimes you can write this as f of n, like this. But this is not to be confused with actually multiplying f by itself. I'm just applying f to itself many, many times. So in other words, this is just f of dot dot dot, where I've nested f inside itself. Nested f inside itself n times. Yeah, so this is kind of an important construction in math, and it shows up in fields, other branches of math, like dynamical systems, where you want to analyze what happens if you iterate a function many times, and whether or not you converge to a particular value, or you diverge away from a particular value. So there's a lot of things in that direction we can investigate. So maybe I should give another example of a recursive sequence, and this is a very famous sequence known as Fibonacci sequence. So what is a Fibonacci sequence? So it's defined by, first of all, it's a recursive sequence, and it's a recursive sequence. So it's defined by specifying the first two values. So it's a recursive sequence specified by the 0th term is just 0, and the first term is just 1. Those are my initial values. Those are given. And the nth term of the sequence is obtained by adding the previous two terms. So it's obtained by adding f of n minus 1 to f sub n minus 2. Okay. So this is our recursive relation. So let's try to write down the first few values of the Fibonacci sequence. So f of 0 and f of 1 is already given to us. Those are 0 and 1 respectively. And to find the next term, you have to add the previous two. So if you want to find f sub 2, you would have to add f sub 1 to f sub 0. So you would get 0 plus 1, which is 1. That tells me that f of 2 is 1. If I want to find f sub 3, that's f sub 2 plus f sub 1, because I'm adding the previous two terms. In other words, what I've written here is just applying this formula here in the case when n is equal to 3. So I get f of 2 is, I know it's 1, and f of 1, I know it's 1 also, so I get 2. That means f of 3 is 2. F of 4, on the other hand, is f of 3 plus f of 2, so it's 2 plus 1, which is 3. So f of 4 is 3. Let's write down a few more terms. F of 5 is f of 4 plus f of 3, so it's 3 plus 2, so it's 5. So f of 5 is just 5. So the Fibonacci sequence, is basically this one. So f sub n, and starting at least at 0, is, so the first term is 0, and then we have 1. And how did we obtain the next terms? So, okay, so this is n equals to 0 term. This is the term that corresponds to n equals to 1. And how did we obtain the other terms? Well, we added the previous two terms. So if I wanted to get this one, I would add these two back. So 0 plus 1 gives me 1. To get this one, I add 1 plus 1, I get 2. To get this one, I add 1 plus 2, I get 3. Then I add 2 plus 3 to get 5. I add 3 plus 5 to get 8. 5 plus 8 to get 13. 13 plus 8 is 21. 21 plus 13 is 34. 34 plus 21 is 55, and so on. So you get this list of numbers. And it turns out, amazingly, there is actually a formula to get the nth term of the Fibonacci sequence directly. Right? So we have a recursive relation that defines Fibonacci sequence here, but what if you wanted to find the 1,000 terms of the Fibonacci sequence? And I'd say I don't want to actually keep writing 1,000 terms like this because it's not efficient. Now it turns out there is a closed formula. So amazingly, for the Fibonacci sequence, there is a closed formula to obtain the nth term. Okay, for Fn, and it's the following. So nth term of the Fibonacci sequence is 1 over square root of 5 times 1 plus square root of 5 over 2 to the power of n minus 1 over square root of 5 times 1 minus square root of 5 to the power of divided by 2 to the power of n. And this is true for any n starting at 0. Right? What is so cool about this formula is that there are some square root of 5s that are floating around. So you might be tempted to think that there's no way this formula could be correct, because maybe like if you expand this and there will be some square root of 5s left, and that doesn't make sense because all these terms in the sequence, as you can see, are just natural numbers. However, it turns out that all these square root of 5s, when you expand, like take the nth power and then subtract according to the given instructions, all these square root of 5s that float around, they actually cancel perfectly. So the result of this operation is in fact a natural number. It's like a whole number. There's no square root of 5s. Anyway, so what this last thing that I wrote here is just an optional material. Okay. And if you want to learn more about Fibonacci sequence and about the history of the Fibonacci sequence, you can read, for example, Wikipedia page about why it's so important in math and why it shows up in a lot of places. Okay, so let's talk about a few more properties of sequences. So here is an important class of sequences known as bounded sequences. So bounded sequences, what are they? Well, basically they're sequences that whose the values of the numbers are just bounded between some real numbers. So it can't get arbitrarily large. So here is a precise definition. So we say that a sequence a sub n, and at least so this is my sequence specified by giving the nth terms. It's bounded if there exists a real number m, capital M, such that the absolute value of a sub n is at most m. So basically what this means is that graphically, right, if you plot, graphically speaking, if you plot the elements of the sequence, so let's say we plot the numbers, so we can plot them by plotting the point n comma a sub n in the usual xy coordinate system. And then the picture looks like this. Then the picture looks like this. So we get the terms, the y values cannot exceed y equals to m, and also y equals to minus m. So basically, like my first term is a sub 1, so maybe it's somewhere here. My second term is a sub 2, maybe it's somewhere here. My third term is a sub 3, maybe it's somewhere here. A4 is maybe here. A5 A5 is maybe somewhere here at 0. So there's my x-axis, my y-axis. A6 could be here, and so on. A7 could be here. So basically, the sequence is bounded means that if you plot the y values as your sequence values, then they cannot escape these two lines. Okay. So, for example, a constant sequence would be an example of a bounded sequence. So, a sub n defined by just 7. Sorry, so this is 7, 7, 7, 7, wherever. this is a bounded sequence. Because we can pick, it's bounded by m equals to 7, because we can pick m to be 7 in this case. Remember, bounded just means that the absolute value of a sub n is less than or equal to m for every n. Okay. So here's another sequence. Say 3 divided by n squared. N starting at least 1. Okay, so what is this? So the first term of the sequence is when you plug in n equals to 1, we get 3 divided by 1 squared, and that's just 3. Then we get 3 divided by 2 squared, so 3 over 4. Then we get 3 divided by 3 squared, 3 over 9, 3 divided by 4 squared, 3 over 16, and so on. So this is bounded. This is a bounded sequence, and it's bounded by, well, we need to figure out what's the biggest value we can get in absolute value, and that's 3, because the 3 is the first term, and everything else is actually smaller than 3, so it's bounded by m equals to 3. Let's look at this sequence. Cosine, say, 3n, or 5n, say. Cosine 5n divided by n. So this is a bounded sequence because you can actually take the absolute values of each term and show that it's less than 1. So cosine 5n over n, certainly less than 1 over n, because cosine of anything is less than 1 in absolute value. So we just get 1 over n because n is positive. And 1 over n is less than 1 because my n is starting with 1 and onwards. So that shows that we can pick m to be 1 in this case. Works. Okay, so what are some examples of sequences that are not bounded? So here's an easy one. So nth term of the sequence is just n. So what is the sequence in terms of lists? So the first term is 1, second term is 2, 3, 4. This sequence is certainly not bounded because the terms get large and large. So not bounded. They get arbitrarily large. Okay, so what does this mean? In other words, to make this precise, there exists no choice of m that works, right? There is no m such that a sub n is at most m for each value of n, because already, if you look at a sub m plus 1, that's by definition m plus 1, and m plus 1 is bigger than m. So that shows that you can get bigger than any particular number eventually, and so the sequence is not bounded. Sequence bounded means that you cannot escape, essentially, certain bounds. You're constrained to be between the lines y equals to m and y equals to minus m. Okay. So here's another definition that's important, and that's monotonically increasing and decreasing. So we say that a sequence is monotonically, so sequence a sub n is monotonically increasing if a sub n plus 1 is at least a sub n for each n. Sometimes we use the word increasing instead of monotonically increasing to save time. And and we say that the sequence is monotonically decreasing, is monotonically decreasing if a sub n plus 1 is less than or equal to a sub n for n starting with 1 and onwards. In other words, monotonically increasing and decreasing just means that the terms are getting bigger and bigger one by one, or you're getting smaller and smaller one by one. Okay. So for example, the sequence defined by just n, so nth term of the sequence is n, this one. So this is 1, 2, 3, so on. This is increasing because clearly the terms are individual. So if you compare two consecutive terms, the one on the right is bigger than the one on the left. And if you look at the sequence 1 over n instead, so this is a sequence whose terms looks like this. So when n is 1, you get 1. When n is 2, you get 1/3. 1 over 2. When n is 3, you get 1/3. When n is 4, you get 1 over 4, and so on. And this is monotonically decreasing because it's clear that in this case a sub n plus 1 is less than or equal to a sub n. But it's basically like the formal verification for the claim that I just wrote would be the following, like a sub n in this example is 1 over n, and since making a denominator bigger makes the number smaller, we know that 1 over m plus 1 is actually less than or equal to 1 over n, but by definition this is a of n plus 1. By definition this is a sub n, so we know that tells us that n plus 1th term is less than or equal to nth term, and that's the definition of monotonically decreasing. So what about this sequence? So -1 to the n over n, starting with 1. So, okay, the first term is when you plug in n equals to 1, the first term of the sequence is -1, because you get -1 to the power of 1 divided by 1, and that's just -1. Then you get -1 to the power of 2 divided by 2, and that's positive half. Then you get -1/3 when you plug in n equals to 3. Then you get positive quarter, and you get -1/5, and so on. So if you plot what this sequence looks like, I mean, you get something like this. So basically, first you have, so at n equals to 1, you get -1, and then at n equals to 2, you get half. Then n equals to 3, you get 1/3. Then n equals to 4, you get positive quarter, and so on. So this sequence is neither increasing nor decreasing. The sequence is neither increasing nor decreasing. So note every sequence has to be monotonically increasing or monotonically decreasing. Some sequences can do that. So just charging the computer. Great. So next thing I want to talk about is very important. It's called convergence and divergence of sequences. So, what does it mean sequence converge? Basically, sequence converging just means that the terms of the sequence gets closer and closer to a particular value. So, convergence of sequences. Okay. So we say that a sequence a sub n converges, if there's a number L, this is going to be the limit, basically. If there exists a number L, some real number L, using the L because it's supposed to denote the limit, such that the terms of the sequence gets closer and closer to L as n gets bigger and bigger. The elements of the sequence gets closer and closer to L as n gets bigger. But it's not just getting closer and closer. Somehow you need to get arbitrarily close to L. You should be able to get near L as close as possible. And so we write this, in this case, we write this in the following notation, which should be familiar to you. So we write the limit as n goes to infinity of a sub n is equal to L. Okay. If there is no such number L, otherwise, we say that the sequence diverges. So if the sequence does not converge, which means that there is no such number L, does not converge, we say that it diverges. We say that it diverges. Okay. So basically diverges just means does not converge. So now let's give some examples of sequences that converge. So, for example, this could be one of them, 1 over n. So this is 1, 1/2, 1/3, 1/4. This sequence converges to 0. Because as n gets closer, and as n gets bigger and bigger, the terms of the sequence gets closer and closer to 0. If you look at -1 to the n over n, this has the terms -1, +1/2, -1/3, +1/4, and so on. This one also converges to 0. The terms are approaching 0 from either side, from both negative and positive, but they're still convergent to 0 because as n gets large and large, we get arbitrarily close to 0. So here's a slightly more complicated looking example, but we actually have the tools to figure out the convergence of this sequence. So if you're given a sequence whose basically nth term is given by this expression. So this is a sequence where the first term would be when you plug in n equals to 1 into this expression. And n equals to 2 would give you the second term of the sequence. And this way you get a list of numbers, so you get a sequence. So this sequence converges because when n gets large and large, the value of this expression converges to 1 over 5. And the way you see that is using what we know from calculus. So limit as n goes to infinity of n squared plus 3n plus 1 divided by 5n squared plus n plus 7. This is limit n goes to infinity. Basically, there's an invisible 1 in front of n squared in the numerator, like so. And the way you compute the limit of a polynomial divided by a polynomial of equal degree, in this case degree 2, is you compare the leading coefficients. When n gets large, the contribution coming from the lower order terms is negligible for all purposes, and therefore the ratio tends to 1/5. And so the sequence in particular converges to 1/5. So here's another example of a sequence that converges. So first term is 3, then you have 3.1, then you have 3.14, then you have 3.141, then you have 3.1415, then you have 3.14159, and so on. And so this sequence, what I've written down here, is the truncated digits of pi. This converges to pi. So basically we can think of the terms of the sequence as rational numbers that approximate pi. So we can think of terms of the sequence as rational approximations of pi. Because they're rational numbers, they're decimal digits n, and they get closer and closer to pi as n gets bigger and bigger of the number pi. And remember that, recall that pi itself is irrational. So pi itself cannot be written as a ratio. Pi itself cannot be written as a ratio of two natural numbers. That's why it's irrational, but we can approximate it by rational numbers by basically truncating the first n digits of pi, and this sequence exactly encodes that data. And so what are some examples of sequences that do not converge? So here's one. So if you look at the sequence given by given by the following data, so the nth term of the sequence is n. So we've seen the sequence many times already today. This diverges because as n gets bigger and bigger, there's no number L that the sequence diverges. Terms just get bigger and bigger. So, but note that there's a something special about this example. This example is not bounded, and that's sort of a very quick reason for why it should diverge. So note that this sequence so I said diverges, but this sequence is somehow worse. So it's unbounded. So it's not bounded. And if the sequence is not bounded, it must automatically diverge. It must diverge. And so maybe we'll talk about this next time. This is because if the sequence were to converge, it must be bounded. If sequence converges, it must be bounded. So, therefore, if your sequence is not bounded, then there's no way it could converge. It must diverge. However, just because the sequence is bounded, it does not mean that it should converge, right? What I've written here is just one implication. If the sequence converges, then it must be bounded. But if the sequence is bounded, that does not mean that the sequence converges. Very important. So for example, consider the sequence -1 to the power of n as the nth term of the sequence. So we have first term is when n is 1, that gives you -1. The next term is when n is 2, that gives me +1. Then I get -1, +1, and so on. Okay, so this is an example of a sequence that diverges, but it's definitely bounded. So note, this sequence is bounded. but it diverges. There's basically the terms of the sequence, they oscillate between -1 and 1, which means that they don't actually get close to any number, any particular value, right? They don't tend to any particular single value. They don't tend towards a single number as n goes to infinity, and therefore the sequence diverges. So basically the punchline I want to say is that a convergent sequence must be bounded. Convergent sequence must be bounded. So in particular, if the sequence is unbounded, it must be diverges. If it's unbounded, it must diverge. And then the second remark is that, so this is the first remark. Second remark is that a bounded sequence may not converge. A bounded sequence may not converge, as we saw above in the second example. Like in this example here, the sequence was bounded, but it didn't converge. So one implication is true. Your sequence converges, that means you're tending towards a particular number, then in fact you must be bounded, because basically near the limiting value you're bounded, and away from the limiting value there's only finitely many values to consider, and so you're bounded. So next time I will maybe give more explanation and in fact proof of the first bullet point here. And I think this concludes the lecture number 18.